All right, what is up, everybody? Today, we're going to talk about sound waves. Now, we've already learned about transverse waves, and this is a type of wave that people are most familiar with, where there's a crest and a trough, and the medium, whenever the wave is traveling through, goes up and down like this. There's an equilibrium position, which is where the string or whatever the thing is would be if it was still, and then the crests are at the top, and the troughs are at the bottom, and the wavelength would be the distance in between two parts of two identical parts of the wave. Okay. Now that's not the only type of wave, right? So if you remember these parts, we're going to look at another type of wave, which is actually probably more common. And that is a longitudinal wave, right? And we're learning about this because we're learning about sound waves, and sound waves are longitudinal waves. So in a longitudinal wave, you don't have the ups and downs. What you have is areas of higher pressure or higher density where the material is closer together. And then you have areas of lower pressure or lower density. Okay, the places of high pressure are compressions, and then the areas of low pressure are rarefactions. So if you've ever seen a slinky like go back and forth like this, there's places where the rings are close together, and that's a compression, and places where the rings are farther apart, and that's a rarefaction. So that kind of corresponds to like the crest and trough that we saw with transverse waves. So the wavelength is still going to be measured from one part of a wave to the exact same part of the next wave. But a wavelength would have to include both a compression and a rarefaction. So if you start at a compression, you have to go through a rarefaction and then to the next compression to get a full wavelength. Now, if you look at the wave at the bottom here, right, these little dots, a sound wave looks more like this, where you can imagine these little dots are air molecules. And with a sound wave, there are areas of the air where the the air pressure is higher, meaning the air molecules are closer together. And there's parts of the air where the air molecules are farther apart. And these are going to go back and forth hundreds of times every second. Right? And that's what creates a sound wave, which your ear is able to interpret as being sound. When we're talking about a wavelength, we're talking about distance from one rarefaction to another or from one compression to another. So if you look at this picture, imagine this is like a tube and there's air inside, and there's a sound wave going through this tube right now because some of the air is really high pressure. There's lots of air molecules, and then some of the air is low pressure. What's going to happen is the high pressure is going to go into the low pressure. The low pressure will become high pressure, and then the high pressure become low pressure, and so forth. A lot of times, it's easier to visualize what's going on if we draw a transverse wave on top of this. Okay. If we draw the transverse wave, it looks something like this, right? Where the high pressure is the crest and the low pressure is the trough. Okay. So sound results in the vibration in air molecules, or it doesn't have to be the air. I mean, sound can travel through um, solid objects as well. Um, but if you imagine that the air around you, if you could see the air molecules, there'd be trillions and trillions of them, but they would be high. They'd be closer together wherever there is a high pressure part of the sound wave, and they'd be farther apart when there's a low pressure. And so, if we just draw the wave where there's a crest at the high and a low um, at the low pressure, then the wave would give us a pretty good picture of what's going on in the sound. So from now on, if you see a transverse wave like this drawn and it's called a sound wave, just know that it's the sound waves don't actually look like that, but it's just a way of visualizing the high and low pressure of a sound wave. Okay, so how do we hear sound? Well, first, a object causes the air molecules to move. Okay, so you have this tuning fork. If you know anything about tuning forks, you hit it on something and it vibrates at a certain frequency. Well, you don't directly hear the tuning fork. What happens is the tuning fork will bump into the air molecules, and it's going to bump into the air molecules with the same frequency that it's vibrating itself. And those air molecules are going to bump into each other, which sends a sound wave off in all directions. Okay, sound waves will go through the air and they'll go in all directions. So whether you're ahead of it, to the right of it, to the left of it, or behind it, the sound waves will go off with the same frequency, same speed in all directions. And this causes there to be a longitudinal wave, okay, with the compressions and rarefactions. And this will go to your ear, right? So if you imagine this tuning fork is 90 hertz, so the thing will vibrate back and forth 90 times each second. That's going to bump into the air molecules and cause the air molecules themselves to vibrate 90 hertz. So it's going to cause a wave through the air that's 90 hertz. Now your ear will pick up on this, and there's things in your ear that will vibrate 90 times per second, and then your brain is going to interpret that as a low pitch sound, okay? Because 90 hertz is fairly low pitched compared to other sound waves that we hear. Now I take a different tuning fork, and sorry about that. Different tuning fork, and you hit it, and it vibrates, say 2,000 times per second. Well, it hits the air, and the air molecules are disturbed at 2,000 uh, hertz, 2,000 times per second, and they bump into other molecules, and so forth. And soon you have a sound wave that's going off into all directions. If your ear is anywhere in this room, then this sound wave will enter your ear. It will vibrate the um, things in your ear 2,000 times per second, which your brain will interpret as a high pitched sound. Okay, so 90 hertz was a low pitch, 2,000 would be a very high pitched sound. So that's how you hear sound. Now, let's talk a little about instruments, specifically stringed instruments. So let's say that there is a guitar string here, and it's a 0.4 meter long string. If you pluck it, and we're told that if you pluck it, it makes a frequency of 200 hertz. What's the wavelength and wave speed? Well, if you pluck it, remember it's going to vibrate most dominantly in its first harmonic. Okay, and so the first harmonic is just when there's one big bump that alternates between a crest and a trough. And so it's going to look kind of like this, where sometimes it's up here, sometimes it's down here. The way that you find a wavelength is by this equation, and that Greek letter lambda is there. Is the wavelength. The uppercase L is the length of the string, and N is a harmonic number. So if you have one bump going up and down like this, that N is going to be 1. And that means the wavelength is just simply twice as long as a string. All right, so this was a 0.4 meter string, and so the wavelength would be 0.8 meters, which makes sense because remember, a first harmonic is just one bump, which is just half of a wavelength. So now we can find the wave speed, and by wave speed I mean how fast is the energy going up and down the string. Okay, and the wave speed could change. Like for a guitar string, it'll change depending on how thick the material is and how tight it's wound. If you go from a guitar string to, say, a rubber band, it's going to change completely as well because it's also dependent on the material. But we're trying to find the wave speed of this particular guitar string, and to do that, you just use this equation. This is wavelength times frequency. We found out that the wavelength was 0.8 and the frequency was 200, which means the velocity of the wave would be 160 meters per second. Okay, so this guitar string will vibrate the air at 200 hertz. The energy will go up and down the string 160 meters per second, and that will shake the air molecules around the guitar, causing another wave to go through the air, and that wave would also have a frequency of 200 hertz. All right, and actually, its wavelength and its wave speed, wave velocity would be different, completely different, but the frequency would be the same. All right, so you would hear 200 hertz from the guitar string. All right, I'll see you all in the next video.